السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم والصلاة والسلام على أشرف الأنبياء والمرسلين. So please don't forget to make the attendance. You need extra 2 minutes for the others to join. Let me go for this recap. So let's start our class. Please don't forget to make the attendance online. So here, analysis of recursive algorithm. We go recap for this one, then we go to our new subject for this for today. So recursive algorithm, general solution breaks problem into smaller version of itself. General case in recursive definition in which a smaller version of itself is called, must eventually be reduced to a base case. Logically, you can think of recursive method having unlimited copies of itself and calling its own code, set of parameters, and set of local variables. Recursive algorithms, if the problem can be solved for n, solve it. Else, recursive apply the algorithm to one or more problems involving smaller values of n. Combine the solution to the smaller problems to get the solution to the original. Consider the following of numbers 24, 88, 40, 37. A list can be defined recursively. A list is a number or a number comma list. So list is number list. So here we have number comma list. And here we have this is the list, and then we have number comma list. Here, this is the list, and here number, comma, list. So here, comma, list, and here number, this one. So here, this is the recursive build of list. Recursive steps, step one, consider the problem computing the sum of all numbers between 1 and n. If n is 5, the sum is 15. The base case is 1, means if n equal 1, return 1. This problem can be expressed recursively as the sum of 1 minus n is n plus if n minus 1. Recursion combined. Okay? We had an example for this for factorial, here for summation. Public sum integer int result, if n equal 1, return 1, else return n plus sum integer n minus 1. This is calling for the function for recursive function to make the summation, sum of integer. So here, sum integer 5, sum integer 4, sum integer 3, sum integer 2, sum integer 1. Here result 1. Here we call 1 sum integer 2 minus 1. So here return 1 plus 1 result 2. So here 2 sum integer plus 3 here 3. Here 3 plus 1 here 4. 4 here plus 1 5. 5 plus 5 10. 10 plus 5 15. So here this is the recursive of this what we call function sum integer. So here we have 2 plus 1 3, 3 plus 3 6, 6 plus 4 10, 10 plus 5 15. Example factorial, we did also factorial. N equal 1 is equal 0, or here n multiply n minus 1 factorial, n greater than 1. So here same here factorial, public static n factorial. If n equals 0, n return 1, else return 0 factorial n minus 1. So here we have this for this one for recursive, and this one for what you call iterative using while. So here same factorial 1, factorial 2 plus multiply 1, 2, here 2 multiply 3, 6, 6 multiply 4, 24. Here 24 multiply 5 is 120. 120, yes. 4 multiply 5, 0, 2, 2 multiply 5, 10, plus 2, 120. So here the result is 120. Fibonacci, we had this Fibonacci. What is Fibonacci? Fibonacci numbers are the sequence of integers beginning with the position in 0. The first two terms are 0 and 1 by definition. Each subsequent terms beginning at n equal to it is the sum of the two previous terms. F0 equals 0, 1, 1, 2, 3, 5, 8, 13, 21, 34. So formula fib n 0, n equals 0, 1, n equal 1. Here, if n greater than 2, we have fib n minus 1 plus fib n minus 2. Plan of analysis of recursive algorithms. Decide on parameter indicated an input size and find the algorithm's basic operation. Check whether the number of times the basic operation is executed may vary on different inputs of the same size. If it may, the worst, average, and best case must be investigated separately. Set up a recurrence relation with an appropriate initial condition expressing the number of times the basic operation is executed. Solve the recurrence or the very least establish its solution order to growth by backward substitution or another method forward substitution. With recurrence relation, many arithmetic functions can be expressed as recurrence relation. Like here, example, n power 2 can be expressed as recurrence relation. A n equal a n minus 1 plus 2 n minus 1, where A1 equal 1, A0 equal 0. Here equal Fn minus 1 plus 2n minus 1. So here, if I have n power 2, n power 2 means here Fn minus 1 plus 2n minus 1. 2 multiply n minus 1. A recurrence relation. So here, if we have three power 2 means 8. So here we call 3 Fn minus 1. We call 2 plus 2n. So here 2 means 6 plus minus 1. So here it will be 5. 5 minus 6 minus 1 will be 5 plus we call this one. Okay, this one will be we call it for 2. 2 will be 1. 1 plus 2n. 1 means 2 minus 1, 1. So here will be 2 minus 1 plus 1 here we call it, and we calculate for Fn minus 1 means call here for recursive. Okay, a recurrence relation is an equation that recursively defines a sequence or multi-dimensional array of values once one or more initial terms are given. Each further term of the sequence of our array is defined as a function of preceding terms. So here we call n. So here n equal to 3, 2, we have 3, 2, 1, 0. Or we can stop in 1, 3, 2, 1, 3, 2, 1. So here we call it 3 times. So the total will be 2 power n power a, 3 power 2 means 8. How we calculate this one? We go here. We'll do same like we did here. So here we assume n power 2 equal, so here we have 3 power 2 equal 8. Let me use this recursive. So here n equal 3. So here means a3 equal a n minus 1. Okay, means call Fn minus 1, a2 plus 2 multiply 3 minus 1. Then here equal. What is A2? A2 is A A2 is A1 multiply plus 2 multiply 1 minus 1. Then here A1 equal to A1 equal to 1. Here A3, A2, here we call A2, then we call this A2 equal to here A2, and here A1 equal A1 equal 1. So now we replace here 1 plus 2 multiply 1 minus 1. So here will be 1, 2 minus 1 is 2. So here 1 plus 2 multiply 1 is 2 minus 1 1. So 1 is 1 2. So here now 2, and here what we have here we call for A3, A2, A1, okay, and maybe we call here, okay, now here A2 is 2 plus 2 multiply 3, 6 minus 1 is 5, here equals 7, and here equal A2, here 1, 2 minus 1, 2 here, maybe I equal here 2n minus 1, 2n. Here made a mistake. Here made a mistake. So 3, 3. Here 1, 2, here 2. I made a mistake here. Let me remove this one because 2n, not 2n minus 1. n is 2, 2 multiply 2. Here we made a mistake here. Two multiply 2. So here 1, 2 multiply 2 is 4 minus 1 is 2 multiply 2, 4 minus 1 is 3. Okay. 2 multiply, here we have so here we have A2 equal A1. What is A1? A1, 1. Okay, 1 plus 3 is 4. Am I right? So 3 power 2 is 9. Sorry, I make here even wrong. 3 power 2 means 3 multiply 3. So 3, not 2 power 3, 3 power 2. 3 power 2 is 9. Okay, please, if I sorry for this mistake. So 3 power 2 is 9. So here we have 4. Okay. 4 plus 5 4 plus 5 equal to 9. Clear how I make it? I will again assume here A3 equal A2 Fn minus 1 to n minus 1. So here A2 plus 2 multiply 3 minus 1 because 3. Now A2, what is A2? A1 plus 2 multiply 2 minus 1. Okay, A1, what is A1? Is 1. So now here 1 plus 2 by 2 minus 1. So here 1 minus 1 will be 3, 4 minus 1, 3. 3 plus 1, 4. 4 here will be here 4. 2 multiply 3, 6 minus 1, 5. 5 plus 4 is 9. So 3 power 2 is 9. Simple equation. We made mistake in simple equation. No problem. Okay, now we go to complete our slides. This one just a recap. Okay. So the Fibonacci numbers Fn, this one for n power 2. This one Fibonacci numbers Fn equal Fn minus 1 plus Fn minus 2 with these values F0 equal 0, F1 equal 1. Explicitly recurrence yields the equations F2, F1 plus F0, F3, F3 equal to 1, 5, etc. like this. So methods of solving recurrence relations. No universal methods exist that would enable us to solve every recurrence relation. There are several techniques, however, more powerful than others that can solve a variety of recurrences. Methods of forward substitution, methods of backward substitution. So here we have starting with the initial term or terms of the sequence given by the initial conditions. We can use the recurrence equation to generate the first term of its solution in the hope of seeing a pattern that can expressed by a closed-end formula. For example, consider the recurrence 2xn minus 1 plus 1 for n greater than 1, x1 equal 1. So here this is the forward substitution. For example, consider the recurrence. This one, to xn minus 1 plus 1 for n equal 1. Here x1 equal 1. So obtain the few first terms as follows. X1 equal 1, x2 equal 2, x1 plus 1 equal 2 multiply 1 plus 1, x3 2, x2 plus 1, 2, 3 plus 1, 2 by 3 here. Because here we have 2x and minus 1. So here 2x2 plus 1. Here x4, 2x3 plus 1 because here n minus 1. So here we have if we notice that here 2xn minus 1 plus 1. Here 2, for 2 we call 1, for 3 we call x2. Okay, for 4 we call x3. Okay, what is xn minus 1 here? X minus 1 is 1. What is x1? Is 1. Here 2 multiply 1 plus 1, 3. Here what is x2? 2 is 3. Okay, now here what is x2 equals 7. What is x3? x3 equal to multiply x n minus 1. X minus is 7. So 7 plus 1, 15. It is not difficult to notice that those numbers are 1 less than consecutive powers of 2. xn, 2n minus 1, 2 power n minus 1. For n equal 1, 2, 3, and 4. We can prove the hypothesis that this formula yields the generic term of the solution B5, B6, either by direct substitution or the formula into B5 or B6 by mathematical induction. Okay. The method of solving backward recurrence relation with exactly as it is implies using the relation in question, we express n minus 1 as a function of x minus 2 and substitute the result into the original equation to get xn as a function of xn minus 2. So here xn equal xn minus 1 plus n and x0 equals 0. Before I continue, just a gentle reminder, please make the attendance online. Make the attendance online. You feature. I will give you 1 minute to make the attendance. Okay, hopefully all of you make the attendance. Now we continue here our backward substitution. Xn x minus 1 plus n x0 equals 0. So here we call xn minus 1 plus n, replacing by n minus the equation yields xn minus 1 xn minus 2 plus n minus 1. So here we replace n with n minus 2. So it will be here xn minus 2 plus n minus 1. Substitution x minus the initial equation, we obtain xn equal xn minus 2 plus here xn minus 1 plus n equal to n, okay, minus 2 plus n minus 1 plus n. Replacing by n minus 2, the initial equation yields xn minus 2 equal xn minus 3 plus n minus 2. So here we replace n minus 2. After substituting this expression for xn minus 2, we obtain xn minus 3 plus n minus 2 plus n minus 1 plus n equal xn minus 3 xn minus 2 plus n minus 1 plus n. Okay, we can do this one easy by just replacing xn minus 1 with xn. We did here an exercise with this one. So here we replace just here xn with xn minus 2, okay, with n minus 2. Then we replace here n minus 1 with x minus 2 with x minus 3, and we got this one. This one, the backward substitution. Okay. So here, what is xn minus 2? Xn minus 2 is xn minus 3 plus xn minus 3 plus here we have to replace n minus 3 by n minus 2, okay, plus here n minus 1. So here n will be n minus 2. So let me do the substitution here. Okay, now here xn minus 1 equal x n minus 1 minus 1 plus n minus 1. So what is equal? X n minus 2 plus n minus here n minus 1 here n minus 1 plus n minus 1. Okay, so here plus n minus 1. Now xn minus 2. So here if I need to see what is xn minus 2 equal, xn minus 2 equal here xn minus 2 plus n minus 1. So xn minus 2 what is equal? Replace x with n minus 2. So here xn minus 3 plus n minus 2. From here, I can see that here that xn minus 2 equal x n minus 2 plus n minus 2. Okay, this one xn minus 2. From here, I can get that xn minus 2, okay, see here, x n minus 2 equal to xn minus 1 minus n plus 1. From this one, xn minus 2 equal xn minus 1 minus n plus 1. And here, xn minus 3 okay. Okay, if I replace here xn minus 1 with xn minus 2 minus 1, here will be, let me here replace xn minus 1. What is xn minus 1? Is xn minus 2 plus n plus minus 1. Let me remove this one. Let me just here xn minus 1, put this one. So xn xn equal, what is x minus 1? Is x n minus 2 okay, xn minus 2 plus n minus 1 plus n equal xn equal to xn minus 2 plus here from where I get this to here xn minus 1 plus n not 0 2 plus n, this n. So here xn minus 2 plus n plus n plus 2n minus 1. xn minus 2, what is equal xn minus 2? Equal xn minus 3 plus n minus 2. This one xn minus 3 plus n minus 2. Okay, this one xn minus 2 plus 2n minus 1 equal what? xn minus 3 plus n plus 2n plus 3n minus 2 minus 3 minus 3. So here we have here xn minus 3 plus 3 plus n. So here we can get that xn equal to here we go back to our slides. Okay, we can make a formula xn minus 2 plus n minus 2 3n minus 3. Here we can get like this. Okay, we can substitute here and get this formula, same formula with different representation. We need to get a pattern. So here we have xn minus 1. So here we replace xn minus 2 plus n minus 1 here, plus n. What does it mean here? Xn minus 2 plus n minus 1 plus n. So what is n minus xn minus 2? Xn minus 2 equal xn minus 3 plus n minus 2. So here xn minus 2. So here will be xn minus 3, okay, plus n minus 1. This is xn minus 2. So this one, okay, xn minus 3 plus xn minus 2. What is x minus 2? X minus 2 is x minus 3, xn minus 2. This one I replace here with 4xn minus 3. Okay, I put it here, xn minus 2. Here I replace x minus 2 with xn minus 3 plus n minus 2. Okay, here plus here, what is here? N minus 1, n minus 1, here this n minus 1 plus n, plus n. So when I get this one, I get xn minus 3 plus n minus 2 plus n minus 1 plus n. Okay? So here we got a pattern. Comparing three formulas of, we can see the pattern arising after I substitution. Xn equal xn minus I plus n minus I plus 1, ni plus 2 plus n. Since the initial condition B2 is specified for n0, we need a0 I equal n to reach it. Xn x0 plus 1 plus 2 plus n equal 0 plus 2 plus n equal n plus 1 divided by 2. Okay, this one from B2. From B2 we got 0 x0. So here we have x0 equals 0. Okay, so here n equals 0, we need n minus I equal 0. That means I equal to n. When I equal to n, we got 0. So x0 n minus I plus 1. Okay, here we have 1. Because here we replace n minus I. 0, 1. Okay, x0 plus 1 plus 2 plus 3 plus n. So x0 plus x1 plus 2 plus 3 will n equal 0. Here x0 will be 0 plus 1 plus 2 plus n, 0, 1, 2, 3, n equal n plus 1 divided by 2. Again, I will go to solve it according to the formula here to get the pattern. Let me share the screen to get the pattern like we did here. You need the pattern. Okay? Yes? Yeah, do you have a question? We need to find the pattern. Okay, here they write a pattern like this. They like a pattern like this. Okay? n minus 1 plus n. Then let me go here. xn minus 2 equal xn minus 3 plus n minus 2. So here equal here they didn't make here n minus 2 plus 2n. They didn't make like this. You make it xn minus 1 here n minus 1 plus n. Here make it like this, x minus 2 xn minus 1 plus n. So he make this like here. He make here parentheses like this. Plus n. Then here he make this one. He didn't calculate make the total. He make xn minus 2. What is x minus 2? X minus 2 is xn minus 3 plus n minus 2. Xn minus 2 is n minus 3 plus n minus 2. We make like this, and he replace n minus 2 with n minus 3. Okay, he make it like this, xn 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 equal xn, okay, xn minus 2 is xn minus 3 n minus 3 plus n minus 2, okay, like this, xn minus 3 plus n minus 2. This one only xn minus 2 plus here n minus 1 plus n. Here xn minus 3, xn minus 2 plus n minus 1 plus n. So here he make like this, xn equal xn minus 3, xn minus 2, n minus 1. Okay, xn minus 3, remove this one bracket. Okay, so for I, he said for x n equal I, he got this formula, n minus 3, n minus 2, n minus 1 plus I. So here we have n minus I plus n minus I plus 1, n minus I plus 2, n here like this. We make this formula. We got the same here. We got the same here. This one is same. xn minus 3, n minus 2, n minus 1 plus n. Now he got this I. He got this I. Like this pattern. He got pattern xn when I equal 3. We'll have n minus 3, n minus 3 plus 1, then is n minus 2, n minus 3 plus 2, n minus 1 plus n. If we have 3, we will got this here. Replace here I with 3. Replace here I with 3. Well, it will be xn minus 3. Here ns minus 3 plus 1 means ns minus 2. Na 3 minus 2 will be n minus 1 plus n plus n. So here this is the pattern. So here we have x if I equal to n I equal to 0, we will have here what we have here n minus if I equal n equal I equal n. To have a x0 I have equal n. If I equal n, we have x0 I plus ni plus n minus I. So here this one will be x0. Here n minus 1 will be 0 plus 1, n0 plus 2 plus n. So here will be here if I here after this got this pattern, if I equal to n, what will we have here? X n minus I means I equal n. So here n minus I equal n. So n minus n. Plus n minus n plus 1 plus n minus n plus 2. Okay? Plus n. So here we'll have x0 plus 1 plus 2 plus n will go with n will we have only 2 plus 3 plus n. x0 we have 0. x0 equals 0 according to our B rule. So here will be 0 plus 1 plus 2 plus 3 will equal this one will equal plus n, and this will have this formula n plus 1 divided by 2. Okay, let us go back to our slides. Okay. Factorial Tn Atn minus 1 plus 1 for n greater than 1, n equals 0. So here we have n here example factorial big O n. Okay, set up recurrence relation for the basic operation. Okay, tn minus 1 open. Here we have big O n. Here big O n also example power. Set up recurrence relation basic operation and find the big O. Here n equals 0, return 1, else return x power x n minus 1. So here we'll have xn equal 1 if n equals 0, x multiply x n minus 1. This is a recurrence of x minus 1. So if x equals 0, if x equal n equals 0, we'll have 1. Result will have 1. Finding the number of binary digits. I think we had this exercise in our chapters in the PowerPoint. We did this one. Okay. Example, recurrence relation. Given the following recurrence relation, find the big O. Tn minus 1 plus 5 for n equal t1 equals 0, or n minus 1 plus n for n equal, greater than 0, t0 equals 0, or n power 2. Okay. Here tn by 2 plus 1, t1 equal 1, O log n. We had some examples and we did some exercises this week in our tutorial. So now we move to the next chapter. Okay, that one's for the mathematics, and now we have only the algorithms. Okay. I'm hearing some noise. I will make a mute for. Okay, can you hear me? Now I mute some of your guys because maybe he opened the mic and he didn't forget to close it. Okay. Design, strategy, and brute force. We go now here in this chapter. It's easy because we did a lot of examples here. So what is design strategies, techniques? An algorithm design techniques or strategy or paradigm is a general approach to solving problems. Algorithmically is applicable to a variety of problems from different areas of computing. So algorithm design technique or strategy or paradigm is a general approach to solving problems algorithmically that is applicable to a variety of problems from different areas of computing. Methods of specifying an algorithm. We have pseudocode, a mixture of natural language like constructs. Flowchart, a method of expressing an algorithm by collection of connected geometric shapes containing description of algorithms steps. We have here, we will go in our course, the rest of our course, we'll go through brute force, we call it exhaustive search, divide and conquer, greedy approach, dynamic programming. We'll go here, and this from now, we will cover these four strategies. Brute force, divide and conquer, greedy, dynamic programming. So, analogy, look at here. Suppose your cordless phone rings, but you have misplaced the handset somewhere in your home. To complicate matters, you have just walked into your home with an armful of groceries and it is dark out, so you cannot really slowly solely on eyesight. Okay, now you are hearing the phone, but you don't know where is your cordless phone, and you have in your arm full of groceries, and it is dark, so you cannot really solely on eyesight. You cannot solely on eyesight. This is the problem. Design one, technique one. To find the ringing telephone, you would ignore the ringing of the phone, or you could not hear it and simply walk over every square inch of your home, checking it to see if the phone was present. So here I ignore the hearing the voice and just go here step by step and go here until I find the phone. So here, to find the ringing tone, you would ignore the ringing of the phone. You could hear it, and you could not hear it, and simply walk over every square inch of your home, checking it to see if the phone was present. You probably would not be able to answer the phone before it stopped ringing. Maybe it stopped ringing before you find it. Unless you were very lucky, but you would be very guaranteed to eventually find the phone no matter where it was. Okay? Okay, even the we are maybe you are not going to able to answer, but you will get the phone. But if you are lucky, maybe you are walking searching for your phone, and you before the ring stops, you find the phone and answer the phone. Okay, this is design technique one. So here we go over all the home, what we call searching for the phone. Maybe if I am lucky, I can before the ring stops, I can get the phone. Maybe I didn't get the phone when it stopped, but I will get the phone even it is not ringing. Sequential search. We call this sequential search. Algorithm 2. A0NK implements sequential search with search K at a sentinel input, an array of n elements, and search for key K. Output the index of the first element is 0 and minus, whose that value is equal to K, or minus 1 if no such element is found. Here an equal K. Okay, this is the key. This is the key. So n equal the key. So here I equal 0, while I not equal K, do I plus 1. If I less than n, return I. Else return minus 1, so I didn't find the key. Bubble sort. Bubble sort, here sort a given array by bubble sort, input an array a n minus 0 to n minus 1 or orderable element, output array 0 to n minus 1, stored sorted in non-decreasing order. This is the input. We have orderable elements, and we have here non-decreasing order or ascending order of the array. For I equals 0 to n minus 2, j equal 0 to n minus 2 minus I, from 0 to n minus 2 minus I, do aj plus 1 less than aj, swap aj and aj plus 1. We have swap. If j plus 1 is less than j, we swap. If the coming value is less than the value we have, we replace, swap. Selection sort, 0 n minus 1 sorts a given array by selection sort, input an array a0 n minus 1 of other elements, array sorted in non-decreasing order. For I equal 0 to n minus 2, min equal I. So here min equal I. For j equal I plus 1 to n minus 1, do if aj less than a min equal j. Swap ai and a min. Here selection sort. I will make a swap only if the index here we compare. If the index is minimum, I will compare. If the value is minimum, then I compare. So I don't compare with each value that like bubble sort. Bubble sort we compare. We did what we call a swap many times. And last time we did the swap 10 times when we have example for 5 elements. We make swap in the worst case 10 times. But here if we have this one, we make swap 2 times. 2 times only in selection sort. Characteristic of this technique: a straightforward approach, usually based directly on the problem statement and definition of the concept involved. Just do it. Impractical for bigger instances, but for small instances is okay. Easy to understand and design. All these tell about brute force. So this is the characteristic of brute force, also known as exhaustive search. Technique 2. To find the ringing telephone, you would take care of the ringing of the phone and initially walk over for each section of your home based on the ringing to see if the phone was present in the section. You probably would be able to answer the phone before it stopped ringing. You would eventually find the phone where it was in the section targeted. So here, what I have here, I take care of ringing of the phone. I initially walk over each section. I make sections of the home, then I will search in each section. Okay, well, when it's section, you probably would be able to answer the phone before it stopped ringing. You would eventually find the phone where it was in the section targeted. So here, this one we call it a problem of size. This one, divide and conquer. So here we have subproblem 1, subproblem 2. We divide the problem in subproblems. Here, n mod 2, n mod 2, n divide 2, n divide 2. Then a solution to subproblem 1. Here, a solution to subproblem 2. Then here I combine this solution to get the original solution for the main problem. So here means divide the problem in subproblems, then find a solution for each subproblem, then combine the subproblems in one solution, and we call it this one. They will give me the solution for the main problem. This one we call it divide and conquer. We have algorithm binary search A0 n minus 1 k implements non-recursive in binary search. Input an array 0 n minus 1 stored in ascending order. So here we have in binary search we have a condition. The array should be ordered in ascending. Should be stored in ascending order. Ascending order to find the search. A search key output an index of array element that is equal to k, the index of or minus 1 if there is no such element. Here we have left 0 r n minus 1, left and right, while L less than r means left less than r, do n equal L plus R divided by 2. This is the mid of the array. If k equal AM, return M. If it is equal to the AM, the index, return M. Else, if k less than AM, go Rm minus 1. go to right equal to m minus 1. Go to left. Else L m plus 1 means go to right. Here go to left, go to right. Else if I didn't get any answer, I return minus 1. Return minus 1. This is the basic approach of binary search. So here I divide the problem. So here, if the key, the key, it is I divide the array into in left and right subtrees, and then I compare with the media m number, which is here the middle of the number. If it is less, I go to the right. If it is high, I go to the left. So this one. If it is less, I go left. If greater, I go right until I find the key. Otherwise, I return minus 1. Look at this. Here we have quick sort. We have something called pivot. We divide this one quick sort. Quick sort. What is here quick sort? AI less than equal P, AI greater than equal P. Here in quick sort, here this one was binary search. Quick sort, we have something called pivot. Pivot is a value. I put this value, maybe here I put this value in the middle. All the numbers after this value is greater than P. All the values less than P is on the right, in the left side. Here not be ordered, should not necessary to be ordered. Here not necessary to be ordered. But here first all the values on the right side will be greater than pivot, and all the values on the left side will be less than pivot. This is the pivot, the quick sort. This is the quick sort. Okay. So binary search, we have quick sort, we have merge sort. Merge sort, what is the merge sort? This one, we have 1, 2, 3, 4, 5, 6, 7, 8. 8 numbers. I divide this array in 2 parts. 8, 3, 2, 9, 7, 1, 5, 4. Then I divide this one in 2 parts. 8, 3, 2, 9, 7, 1, 5, 4. Then I divide here A3 in here A3 2 9 7 1 5 4. Can I divide more than this? No. This is the sub problem. Now I merge. I merge if it is less than. I compare here 3 8. Then here 2 9 will be same. 7 1 will be 1 7. 5 4 will be 4 5. Now I merge these two. According to the merge, 2 here, 2 will be 2, then 3, then 8, then 9. Here, 1, 5, 7 will be 1, 4, 5, 7. Then I merge here. So 1 will be the first, 2 will be second, 3, 5, 5, 7, 8. This merge sort last time or last semester, the students they didn't solve this question correctly. They didn't solve this question correctly. I did give question this one and asked them to answer it. They didn't answer this question correctly. They lost the mark just only in this simple question. For merge sort. Characteristic of this technique: divide instances problem into 2 or more smaller instances. Solve smaller instances recursively. Obtain solution to original larger instances by combining these solutions. The most well-known algorithm design strategy. All these tell about divide and conquer. decrease and conquer, or sometimes called decrease and conquer, or transform and conquer design technique. Decrease and conquer, and transform and conquer. This one you got divide and conquer. Make problem in sub problems, then solve each problem. Then we combine the solution of each sub problem to find the solution for the main problem. Technique 3, to find the ringing phone, you would simply be to walk in the direction of the ringing of the phone until you found it. The problem here is that, so here you are, find the thing, you simply walk in the direction of the ringing of the phone until you found it. The problem here is that there may be a wall or an expensive and fragile vase here, we have vase here between you and the phone, preventing you from finding it. So here we have something, and we I hit the phone, and I know the phone, but because of the darkness I cannot see what is in front of me. Maybe I break this vase. So here we have coin change problem. Okay, what is the coin change problem? If I have, how can a given amount of money be made with at least number of coins of given denomination? Example, okay. Now this is the notes that I have in my currency. I have note of 20, note of 10, note of 5, note of 1. Simply, I will show you here. This here, this simple here we have, here you will see here we have 20 ringgit and 10 ringgit. Do you see? Let me show the screen here. So we have 20 ringgit, we have 2 ringgit, we have 5 ringgit, and we have 1 ringgit. Okay, we have these notes. Okay, these notes. I need, if the remaining, I need to give you, if you buy something from me, buy something from me, I want to give you the remaining. You give me 100, you buy something, and the remaining change is 36. What is the least number of coins that I can give you? So I will give you notes of 20, the bigger one. Then I will give you note of 10. Then I will give you note of 5. Then I give you note of 1. This one is 36. This is one solution. Okay, if I give you here another solution, this is not the best answer will be. Let me check if I have here. Maybe I give you here 2, 5. Okay. Okay, here 1, 2, 20. Okay. How many? Well, you said 36. Am I right? So here I have 30, and this 1, 2, 3, 4, 5. Assume this one 6, 1. So here I have 36. Okay, I have 36. But what is the problem? That this one I have how many coins I have? 1, 2, 3, 4, 5, 6, 7, 8. 8 nodes. I need to give you the minimum number of nodes. So minimum number of nodes means 20, 10, 1, and 5. This one will be the best one solution to give you 36. Okay, this one we call it coin change problem. Coin change problem. Here, this one, the coin change problem that I have to give you. So I have give you the remaining change with the minimum number, with the least number of coins. Least number of coins. So here I have, this is the coins 20, 10, 5, 1. So 36 will be 20, then I give you note of 10, then note of 5, note of 1. So how many notes I give you? I give you 4. 20, 10, 5, 1. So here, D1, 20, can C, D2, 10C, D3, 5C, D4, 1C, and the number is 36C. So here, this is the one I give you that change. Hopefully, it is clear the problem of coin change. Now, we have another algorithm, the Dijkstra algorithm. It is a shortest path problem. Very problem here. I have many routes. I want to find the shortest path from the source to the destination. What is the shortest path? Given a weighted connected graph, G, find shortest path for source vertex to search of the other vertices. Single source, single destination. Find a shortest path from a given source, vertex S, to each of the vertices. Single pair given two vertices, find the shortest path between them. So here we have here, this is the weighted. So here, if I from A to B, the cost is 10 ringgit. From moving B to 2 is 2 ringgit. From here, from B to C, cost is 4 ringgit. Here, parking here, 7 here. Okay, this is the what we call the Dijkstra algorithm. We will study the Dijkstra algorithm. We will study the Dijkstra algorithm. So how we weighted algorithm and how we solve this kind of algorithm. How to find the shortest path, and with the lowest cost. Okay, with the lowest cost. So here, if I have to find here 10, 1, 11, 11, 2. If I want to go to E, which is the best route? 10, 11, 2, 13, 2, 10, 12, 12, 7. 19. Oh, this one maybe here. This one A, B, C, E. Yeah, this one goes from A to E. This is the best route. How to find this? We'll study here in this course. Characteristic of this technique constructs a solution to organization optimization problem. So here we don't look for only solving the problem. We need to optimize the problem. Means I can give you the remaining change coin. I can give you a 36 ringgit, but with many notes, maybe 6 notes of 1 ringgit. Okay, maybe 5 and 1. So only two notes, 5 note and 1 with 6 ringgit. So here I can give you here. This is the optimization problem. So construct solution optimization problems piece by piece through a sequence of choice that are feasible, locally optimal, irrevocable, not able to be changed, reversed, or recovered. Feasible, locally optimal, irrevocable means not able to be changed, reversed, or recovered. For some problems, yields an optimal solution for every instance. For most, does not, but can be useful for fast approximation. All these about greedy design techniques. So we talked about brute force. like bubble sort, like a sequential sort. Then we go to divide and conquer, like merge sort. We divide the problem in sub problems. Then we go to changing coin problem. We call it greedy approach technique. Then we go to technique 4, dynamic programming. Technique 4. Recall definition for Fibonacci. Fn equal Fn minus 1 plus Fn minus 2. F0 equals 0. F1 equal computing the nth Fibonacci number recursively top down. Here we call Fn minus 1 plus Fn minus 2. I give you here the problem of this one last time. Here we have Fn minus 1, Fn minus 2, Fn minus 3. Here Fn minus 3, Fn minus 4. So we notice that here I calculate the solution for Fn minus 2 here. Also here I repeat for n minus 2. And here Fn minus 3, I repeat here Fn minus 3. So here this is the problem of Fibonacci. Last time give me the result, but I need to optimize. Fibonacci, here we have to find how to solve this problem. If n equal 1, return 1. If n equal 2, return 1. Return Fibonacci n minus 1, Fibonacci n minus 2. Okay? Here 5, 4, 4, 3, 2, 3, 2, 1, 2, 1, 0. 5, 5, fib 3, fib 1, 2, fib 2, fib 1, 0. So here all this one is repeated. 5, fib 3, fib 3, fib 2, here fib 2, and here fib 2. How many times? 1, 2, 3 times I calculate fib 2. So wasting the money and wasting the CPU and the resources. So how to solve this one? If Fibonacci n equal 1, return 1. If n equal 2, return 1. Fibonacci not equal 0, return fib n, already calculating. Fibonacci n, return fib n. Fibonacci n minus 1 plus Fibonacci n minus 2. So here in this algorithm, I will solve the problem of Fibonacci. No need to calculate this one again. With this algorithm, no need. Last time we said if n equals 0, we have 0. If n equal 1, we have 1. Otherwise, we call Fibonacci minus 1 plus Fibonacci minus 2. But here, no, we have if n not equal 0, return fib n minus 1. So here we have already calculated Fibonacci n. That's why we can use this one, this algorithm, as a dynamic programming to overcome this problem of Fibonacci of recalculating. Characteristic of this technique, main idea, set up a recurrence relating a solution to a larger instance to solution of some smaller instances. Therefore, big recurrence relating solution for large instance of solution. Solve smaller instances once, record solution in a table, extract solution to the initial instances from the table. So here we have a table. We make this result in this table and use this table to solve the problem. So no need to repeat and recalculate these numbers again. A design technique for solving problems defined by recurrences with overlapping sub-problems, invented by American mathematician Richard Bellman in the 1950s, solve optimization problem. So greedy approach and dynamic programming for the optimization problem. All these all about dynamic programming. Programming means planning, not programming means coding. Okay, brute force. We start with brute force. What is brute force? A straightforward approach usually based directly on the problem statement and definitions of the constraint involved. Example, computing a power n, a greater than 0, n non-negative integer. Okay, maybe here equals 0, n equals 0, and non-negative integer. Computing n factorial, multiplying two matrices, searching for key of a given value in a list. This one, some examples, and you can use brute force to this one. Brute force sorting algorithm, selection sort. Selection sort scan the array to find its smallest elements and swap it with the first element. Then, starting with the second element, scan with the elements to the right of it to find the smallest among them, and swap it with the second element. Generally, on pass I here, I less than equal I less than equal n minus 2. Find the smallest elements ai n minus 1 and swap it with AI. So here we have AI minus 1, I min, A n. So here we replace A min with the minimum in their final position 7325. Here we have to we compare 7 with the rest, and we compare if it is a minimum. What is the minimum value here? Is 2. We replace with 2, 7. Then we go with second number, we replace. Okay, like this. We don't swap like bubble sport. We swap with this one, 7, 3, or we swap here 3. 3 is less than 2, we swap 2. 2 is less than 5, no. Here we swap one time. We find the smallest value and then we swap. A list of selection sort A0 n minus 1. Sorts a given array by selection sort. Input an array 0 n minus 1 of orderable elements. Output array 0 n minus 1 sorted in ascending order. This is the output in ascending order. For I 0 n minus 2, minimum equal I. For j, I plus 1 to n minus 1 do if aj less than a minimum equal j. Then here after that we swap ai and a min. So here if it is less we swap. We don't swap like we do in bubble sort. We compare the minimum index with j, and if the minimum is j, the index will just make swap with the ai. Here we want to say what is the time efficiency, space efficiency, stability. Okay, we will do this one in selection sort. We will do this one in our example for bubble sort, and we did this one for the selection sort. So here selection sort only if it is minimum. Okay. Example. Example bubble sort. I think it is easy, but I will repeat here for some of you. Maybe they are confused between stages. If you have this array 9, 8, 7, 5. If we have bubble sort, we'll compare n with 8. Then we 8, 9. This one bubble sort. So here we compare each element with them. 9 with 8 is greater? No, yes, replace 9, 8, 7. 7, no need for bold. 7, 5. Then we compare 8 with 7. We compare 8 with 7. Then 7, 9, 8, 5. Then we compare 7 with 5. So 5, 9, 8, 7. So this is the how many swaps we did? 1, 2, 3. Now here we go here. Now 9 with 8. So here we have 5. Now I finish here comparing with the first time. Now 9 with 8. We have 8, 9, 7. Then we have 8 with 7. So we have 5, 7, 9, 8. Then, okay. Now we compare 5, 7, 9 with 8. So we have 8, 9. So how many swaps we did for these four items? 1, 2, 3, 4, 5, 6. 6 swaps to find the sort. Here in selection sort, here we have same 9, 9, 8, 7, 5. So here we find 9 with which is the smallest value, minimum value? 5. So we replace with 5. 5, 8, 7, 9. Now we find 8. What is the minimum value of the 8 value? What is the lowest value? 7. So here 5, 8, 5, 7, 8, 9. Okay, now how many swaps we did? How many swaps we did? Only 2. Here we did how many swaps? 6. Here, this item with the minimum item. What is the minimum item? Is 5. So here 5. Now 8 with the minimum item. What is the minimum item? Is 7. So we replace 7. So here we have the this is selection sort. Brute force string matching. We have pattern, a string of m characters to search for a text, a longer string on n characters to search in. Problem, find a substring in the text that matches the pattern. So I have string and I have a text. I want to search if this string is in the text. Brute force algorithm align pattern to beginning of the text, moving from left to right to compare each character of pattern to the corresponding character in the text until all characters are found to match successful search, or a mismatch is detected. 3. While pattern is not found and the text is not yet exhausted, realign pattern on a position to the right and repeat step 2. So here we are finding 0011 001011. This is the text 1000 here. Pattern here here we have this one here. I want to find this one. Here pattern happy. It is never too late to have a happy childhood. Here, so I will start with H with I. I compare. I will not here. I start H with T, then with space, with I, with is, until I find here H is match. Yes, I go to the next one. This one we call it the brute force matching problem. String matching. Here, brute force string matching. This is the algorithm T0 n minus 1 P n minus 1 implements brute force string matching. Input an array T0 n minus 1 for n characters representing text and an array is P pattern. This is the text and this is the pattern. of M characters representing a pattern. So I need pattern and we have text. I have this text and I have pattern. I want to see this pattern. Is including in the text? Like example here, happy is in this text or no? This binary code is in this text or no? So here we have this output. What is the index of the first character in the text that starts with the matching string, or -1 if search is unsuccessful? So I'm searching for a string if it is in the text. Here, this is the algorithm for I equals 0, n to n minus m. Do j equals 0 while j less than m and pj equal to ti plus j. Do j equal j plus 1. If j equal m, return I. Here, else return -1. This is one for finding the brute force string matching. So here, I0, start I0, J0, n minus m. While here, while loop, j less than n, pj, okay, equal ti plus j. So here I'm comparing with the letter. If it is okay, the first letter is okay, I compare the second letter. Second, if jn, okay. If it is second letter is okay, okay. If it is not there, return -1 means not in the text. Here, nobody noticed him. Here we do like this example of brute force the pattern characters that are compared with their text counterparts are in bold type. So here I compare N O T. Here I compare here N O T. Here N O T. Okay, here N O T. N O T, N O T, N O T, N O T, N O T. I find here N O T. I return the index of this here. If I say 0, 1, 2, 3, 4, 5, 6, 7, so I will return the index of n because I found here N O T. This is the algorithm that we did. Closure pair problem. Find two closest points on the set of endpoints in the two-dimensional Cartesian plan. Brute force algorithm compute the distance between every pair of distinct points and return the index of the points for which the distance is the smallest. So here I make comparison between all these points and I need the closest pair, means which is the closest pair. So here, according to this graph, this is the closest pair. How to find in closest pair using brute force? I compare each point with the other, and then when I compare each point with the other, and I pick the smallest distance. Closest pair brute force algorithm. Brute force closest points. If A list P list P of n greater than 2 points, P1 xy means the coordinator of P1 and coordinates of Pn xn yn. So this is a list. Output indices of index 1 and index 2 of the closest pair of points. D minimum infinity. For I equal 1 to n minus 1, do. For j equal I plus 1, do. If the SQRT, here, this one, to find the distance. SQRT xi minus xj power 2 plus yi minus yj power 2. This is x. Why I'm using SQRT rather than make the distance like this? If 5, this one in the, if I have this one in 5 and 3, 5 minus 3 is 2. Why I'm using power 2? Means if this position means in we have this position have negative value and this position have positive value. So what is the difference between them? Okay, if I have minus 2 and 2 plus 2, the distance is 4. So how to get this one? I make power. I make power of this one minus 2 power 2 plus 2 power 2 minus 2. It will give me 4. If I say here only minus 2 plus 2, okay, with minus 2 minus 2, minus 4. How this distance is minus? Okay, this one, why I use scarcity is square root for xi minus xj, yi minus yj. Scarcity is square root function. If d less than d minimum is equal d, index 1 I, index 2 j. So here I find the minimum d. Minimum, the points of d will give me the minimum value. Okay, d minimum d. To return index 1, index 2 means the 2 points. The 2 points, point 1 and point 2, according to the index. Index 1 and index 2 means these points are closest pair. Brute force strength and weakness. Strength, wide applicability. Simplicity, yields reasonable algorithm for some important problems: matrix multiplication, sorting, searching, string matching. Weakness, rarely yields efficient algorithm. Some brute force algorithms are unacceptably slow, not as constructive as some other design techniques. Okay, we stop here for today. I know that it was a long session for today, but hopefully you understand what is the problem and how to overcome this problem. Okay? Any questions so far? So here will give me the pair x1, y1, which are the two closest pair. Okay. Please don't forget to make the attendance. Don't forget to make the attendance. Any questions so far? Any questions so far? When you okay, we'll make the we'll discuss our midterm test. When will be our midterm test? We'll discuss when will be our midterm test. Next week, inshallah, we'll discuss. But now next week is week 7. Week 5? Am I right? So we'll discuss in week 5 when I think week 7 will be the midterm test, unless I change, we make it in week 6 or in. I want to know when, if there is a convocation or something like this, will interrupt us from our test. So hopefully in week 7 we have the test. I will inform you when the test will be and send you WhatsApp and group when will test will be. Okay. So if there is no question, we can stop here. Thank you very much for your attending.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Thank
Okay,
you, Doctor.
welcome.
Thank you, Doctor.
Welcome.
Doktor.